Hi everyone. So in today's video, we are going to talk about this really amazing concept. It's called Sandwich Theorem, or sometimes it is also called Squeeze Theorem. As you can see, both these names are really peculiar in nature, and we will see why do we have this interesting name for this theorem. The idea behind this theorem is very simple, purely based on common sense, and you don't need any complex mathematical understanding to appreciate the theorem. Let's see what does it say. The theorem says that let's say we have three functions fx, gx, and hx, and the middle function gx is always sandwiched between f and h, or it is bounded between these two functions. And that's why we are calling the theorem as sandwich theorem. And we can say that the function gx is squeezed between the functions fx and hx. The theorem says that if we have these three type of functions and for some value x equals to a, the upper function and the lower function, both these functions approach towards the same value. Let's call that value as L. So if both the upper function and lower function is approaching towards the same value L, the sandwiched function gx will also approach towards the same number L as x approaches to a. This is Sandwich theorem. You can see purely based on common sense. You don't need any complex mathematical ideas to understand it. Now, what exactly are we trying to say in layman terms? I'm saying that let's say I have a function fx which is lying between, let me take two simple examples. Uh, one is, let's say, x square, and other is 1 minus e raised to the power x. I don't know what exactly is function fx, but I'm just saying that the function fx always lies between these two functions, and I'm interested in finding the limit of fx when x approaches to 0. So I can say that whatever this limit is, it has to be less than the limit of x square for the same x approaches to 0, and it has to be greater than or equal to limit of 1 minus e raised to the power x for the same x approaches to 0. And the idea is, if by chance both these limit come out to be equal, in this case both are coming out to be 0. So since our function is sandwiched between 0 and 0, it has no option but to take the value 0. Right? This is the idea. Very simple to understand. Let's take a couple of examples. I will illustrate this theorem using one or two analytical examples, and we will see the same idea using the graphs also. And this is the example that we are going to see. We have the graph of this function as well. So let's see. We have to evaluate the limit x approaches to 0, x square into cos of 1 by x. So how do we apply Sandwich theorem here? To apply Sandwich theorem, we need some kind of relation between these three functions. So what we are going to say here is that we have a cosine function cos of 1 by x, and we know that doesn't matter what is the value of x, it is small or large, it really doesn't matter. We know that cosine always lies between 1 and -1. Cosine is a bounded function. So if cos of 1 over x lies between -1 and 1, I can say that x squared cos of 1 by x is always going to be less than equal to x squared and greater than equal to negative of x squared. Basically, what I have done in this inequality, I have multiplied x square from left to right. So this is what we are getting. Now you see, as x approaches to 0, as x approaches to 0, we know that this left function, let me call it h, and this function as f, and this function is our gx. So as x is approaching to 0, limit of hx is also approaching to 0. In this case hx is negative of x square. When you substitute x equals to 0 in this expression will approach to 0. And the same goes for limit of fx. Our function fx is also approaching towards the same number 0 as x approaches to 0. So I can say the function x square into cos of 1 by x is sandwiched between 0 and 0. And if it is sandwiched between 0 and 0, this is also going to take the same limit, which is equals to 0. Really easy to understand. If a function gx is less than equal to 5 and it is also greater than equal to 5, then the only possibility is that gx has to be equal to 5. This is the foundational idea behind this theorem. And let's see, let's try to understand it using the graphs as well. I have I have a graph here, and this graph consists of we can say mixture of three graphs. The red graph, the upper one, it is a graph of x square. The lower one is the graph of negative x square, and the middle one is the graph of x square cos of 1 by x, the green graph. And we can see that as we approach towards x equals to 0, the difference in the values of these three functions is very difficult to see, because all the three values are approaching towards the same number 0. We can see this graph one more time here in a slightly different angle. Here also you can see that the middle graph, the green one, which is the graph of x square cos over 1 by x, this graph is slowly but surely going to merge with the graphs of x square and negative x square as we approach towards the origin x equals to 0. So this was one example of Sandwich theorem, very simple to understand. Let's see one more example. We have limit x approaches to sine of 1 by x. Sine is very similar to cos. This is also a function whose values lies between negative 1 and 1. So I can say that x into sine of 1 by x will always lie between the graphs of fx equals to x and hx equals to negative x. So in the red color, we have the graph of x, this red line, and the blue line is the graph of negative x, and the green colored curve or graph is the graph for the function x times sine of 1 over x. You can observe two very interesting things in this graph. One thing is that as we are approaching towards 0, the oscillations of this graph are increasing really fast. I'm trying to say that when x is a very small number, and if you change that number, the graph of sine 1 by x fluctuates between x and negative x in a very fast frequency, in a very fast manner, right? And we can see from this graph that at x equals to 0, the graph of fx equals to x, hx equals to negative x, and x sine 1 by x, all these three graphs are merging at x equals to 0. So I can say that this limit is coming out to be 0 at x equals to 0. So these two are very interesting ideas, and these were interesting because we can sketch the graph of these functions. But sometimes, like the next example that we have here, we have these kind of discontinuous functions whose graph we cannot plot. And even if it is not discontinuous, then also its graph is really difficult to plot, even for this function. So what do we do here? We have to evaluate the limit and approaches to infinity. And in the numerator, we have sum of n number of terms, something like this. And every term is equals to greatest integer of 1 square x, greatest integer of 2 square x, greatest integer of 3 square x, and so on. How do we solve this question, and how do we apply the Sandwich theorem here? One interesting thing here is that without applying Sandwich theorem, I don't think you can actually solve this limit. Give it a try, pause the video if you want to try, and you can give it a try, but it will be very difficult. So let's try solving it. First and foremost thing, I will express this limit in a more compact form. And since we have summation of n number of terms, I can use the symbol sigma. Sigma of greatest integer of k square x, where is k is varying from 1 to n, and in the denominator we of course have n cube. Right? This is a compact form, looks much less menacing than the original form. Now, how do we apply Sandwich theorem? So, to apply Sandwich theorem, you need to be aware of a very interesting property of greatest integer functions. And the property is something like this, that if we have a number y, then the greatest integer of y is always less than equal to the number y itself, and it is always greater than the number y minus 1. I'm trying to say that let's say we have a number, any number, it could be 8.9. So the greatest integer of 8.9 is going to be less than equals to 8. and it is going to be greater than 8.9 minus 1, that is 7.9. And we can verify it very easily. The greatest integer of 8.9 is basically 8, which is less than equals to 8, and it is obviously greater than 7.9. So this particular property is going to be very helpful in our example. Let's see how we are going to solve it. We have greatest integer of k square x, and I can say that greatest integer of k square x is always less than equals to k square x, and it is always greater than the number k square x minus 1. So we can say something like this, and we can apply the sigma in this inequality. Sigma is just summation of terms, it's not anything really big deal. And we can apply the limit in this whole expression as well. So I can say that limit n approaches to infinity, sigma of k square x minus 1 over n cube is less than limit n approaches to infinity, sigma of k square x greatest integer divided by n cube, and this is less than or equals to limit n approaches to infinity, sigma of simply k square x without the greatest integer part. This is very similar to what we saw in the last few examples. We can call this as g of something. We can call this as f, this as g, and this one as h actually. So I'm saying that h is less than g and g is less than equals to f. So if we evaluate the left hand limit and the right hand limit, or the upper limit and the lower limit, and if both these limits come out to be a same number, then I can say the limit of the middle expression, which we are really interested in, that limit is also going to be same. So let's try that. Let's try to evaluate the limit of f. We have limit n approaches to infinity, sigma of k square x divided by n cube. Don't forget, k is varying from 1 to n. And one more thing, since our variable is k, we can pull out the term of x outside the summation. Remember that sigma is very similar to integrals. So we will get limit n approaches to infinity x times sigma of k square. The formula for sigma of k square is n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6. And we already had n cube in the denominator. This limit is super easy to evaluate. Since n is approaching to infinity, and in the denominator, the highest power of n is coming out to be 3. So we are just bothered about the coefficient of n cube from the denominator. That is coming out to be twice of x. And in the denominator, we have the coefficient of n cube as 6. So our limit is coming out to be x over 3. I'm not going to really elaborate how we are going to calculate this limit. It's super easy. If you want to understand how do we calculate these kind of limits, you can watch my other videos where I teach about basic concepts of limits. Yeah, so this limit is coming out to be x over 3. And let's try to evaluate the left hand limit also. The left hand limit was limit n approaches to infinity, sigma of k square x minus 1 over n cube. We already know the limit of this part, it was x by 3, minus we can evaluate the limit of this part also, x over 3 minus limit n approaches to infinity. Sigma of 1 is simply n. So this limit you can find out, n over n cube is coming out to be 1 over n square, and since n is approaching to infinity, this term is going to vanish, or this limit is coming out to be 0. So we have the limit as x over 3 minus 0. We can very easily see that both these limits are coming out to be same. The limit in the left hand side, the limit in the right hand side, both are coming out to be x over 3. So we can say that limit of our original expression, greatest integer 1 square x plus greatest integer 2 square x up to greatest integer of n square x divided by n cube, this limit is less than equals to x over 3, and this is also greater than equals to x over 3. So the only possibility is that our limit is equals to x over 3. So this is our answer. X over 3 is coming out to be the limit of this huge expression. And you can see that using Sandwich theorem is purely based on common sense. You don't have to You don't have to mug up any kind of formula to solve these kind of problems. I really hope that you guys enjoyed this video. I had fun solving these problems. These problems do look a little different than our regular limit problems, but really fun to solve. So if you like the video, yeah, don't forget to share it with your friends. And if you have not subscribed the channel yet, please do subscribe it. Thank you very much for watching. Have a great time, and I will see you around in the next video.